Good evening, and welcome to The Sky at Night, or partly The Sky by Day, because we're going to discuss the sun, with the latest news, and then the sizes of the stars. But first of all, our usual news notes and some amazing news from the inner solar system. The little asteroid Itokawa has been visited by a space probe, the Japanese Hayabusa, and they thought it had failed to land, but of course it hasn't.
No, it's a remarkably ambitious mission, this. It's designed to land on the surface of the asteroid and come back, bring back material. And they got a nasty shock when they got there. It's a horrible, rocky place, which makes it difficult to land.
And no craters.
No, absolutely, but just jagged rocks, which make it very difficult to land. Now, the lander did reach the surface.
But didn't fire its missile.
That's right. It's designed to fire a projectile, maybe a couple of marbles, into the surface, throw up dust, which is carried back to Earth.
And that didn't work.
No, that was the first attempt. But they sent their little probe back down to the surface, and the second attempt was a success, and hopefully the dust will now be on its way back to Earth.
And now let's go far beyond the solar system, and this is your territory, Chris. Einstein rings.
Absolutely. These are beautiful images, but they require some explanation.
They do
Einstein's theory of relativity tells us that light is bent when it's near a massive object, and these are the best examples of this in the universe. What's happening here is two galaxies are lining up exactly, so that the light from a distant galaxy, as it travels towards us, is bent and distorted by the nearby galaxy.
And it's got to be exact too.
Yes, the lineup has to be exact, forming these rings. Now, because the lineup has to be exact, we've only ever found a couple of these Einstein rings before, and suddenly a new survey called SLACS has discovered 8 more, and there's many more to come. And the nice thing for astrophysicists is that the amount the light is bent tells you about the way matter is distributed in the galaxies that we're looking at. So we can use this to probe the astrophysics of the galaxies, how much dark matter there is, and all these other interesting questions.
Dark matter, that of course is the main problem today. What is dark matter? We've no idea.
No, but we can see its gravitational effect, and one way to do that is to look at these beautiful Einstein rings.
Chris, thank you very much. And now on to our main programme. What is the nearest star? People will say Alpha Centauri. Wrong. The nearest star is our own Sun, 93 million miles away, a very ordinary star, but the only one close enough to examine in close detail. So in studying the Sun, we're learning more about the other stars. And 10 years ago, a special solar probe was launched, SOHO, and we're going to talk about that now. And I'm delighted to be joined by two of our leading solar experts, Dr. Lucy Green and Professor Richard Hedison. Welcome to The Sky at Night. Now, first of all, may I come to you, Richard? What exactly is SOHO? Where is it? And what's it going to do?
SOHO is the Solar and Heliotropic Observatory. It's really the world's flagship solar physics mission. It's a space-based solar observatory. It's a 2-ton spacecraft with instruments that basically take the sun to pieces, look at the sun in many different ways to study it right from the core through its atmosphere to its effects in space.
And where is it now?
SOHO is basically orbiting a strange position in space called the L1 Lagrangian point, which is between us and the sun. It's 4 times further out than the moon. The gravitational forces of the sun and the Earth allow a balance. And from that point, you can view the sun 24 hours a day, 7 days a week. The Earth doesn't eclipse you, so it's a wonderful place to study the sun from.
And Britain has played a large part here.
Britain has certainly played a large part in this. We led a consortium from the Rutherford Appleton Laboratory to build an instrument called the Coronal Diagnostic Spectrometer on SOHO. We have an operations facility actually on site in the UK. Another instrument on board was partly built at the University of Birmingham. But the other instruments, even though we didn't build those, there are UK scientists involved in all of them. The UK has really been involved with SOHO.
Well, SOHO has now been operating for 10 years. What do you think are the main achievements of SOHO so far?
There's been so many. I mean, for me, it's looking at the coronal mass ejections, and SOHO has really put coronal mass ejections on the map. These are the very large bubbles of gas and magnetic field that are thrown away from the sun up to speeds of maybe a few thousand kilometres a second, and they basically contain a portion of the sun's atmosphere threaded with magnetic fields, and they can be thrown in any direction at all. But what SOHO has done is it's enabled us to see the coronal mass ejections through the solar cycle, see how the numbers vary, how they rise and fall with the solar cycle, and also we've been able to look at these coronal mass ejections known as halo coronal mass ejections, and these are the ones that are aimed towards the Earth, so we can actually get some advance warning of what's going to hit us.
You can have 1,000 million tons of gas in one of these eruptions. So they're very, very significant in terms of the structure and evolution of the sun's atmosphere, and as Lucy says, the impact on the Earth as well is quite significant because they carry the magnetic field. The Earth has a magnetic field, we live on a magnet, and if you put two magnets together you get an effect. So we have things like the aurora generated, and problems with navigation systems, communication systems, satellite control systems. These are all things that put a price tag on trying to predict these events.
We're learning more too about the actual structure of the sun.
The sun is a bit like a huge bell, and it has sound waves that are bouncing around inside the sun, and it's allowed us to probe the interior. And we have very good models now of the core of the sun moving out through the radiative zone and the convection zone. And what SOHO has done actually is allowed us to see these flows inside the sun, particularly at the bottom of the convection zone where we think the magnetic fields are being created. Then also using SOHO we can move up to the surface of the sun, or the visible surface, the photosphere, and then using different instruments we can move up through the chromosphere and up into the corona as well. And lastly, using the coronagraphs we can see the very, very extended atmosphere and magnetic fields of the sun.
We must remember that SOHO is looking at the sun in different wavelengths.
That's absolutely right, and the point about that is that you can see the corona, and if you can pick out the sun's atmosphere in different forms of light that are coming from the sun, you can actually see radiation from different plasmas that exist in the sun's atmosphere, and therefore different temperatures. And what you see is this writhing sort of spaghetti of loops in front of your eyes, and you can pick out the temperatures that each of these exist at, the gases are within those loops.
Sometimes we talk about the sun being a bit like an onion, so you have different layers at different temperatures. So that's why you really need these different instruments to be able to see the different temperatures and the different layers of the sun. And also when you're looking at different phenomena on the sun as well. So for example, we want to be able to see the sources of coronal mass ejections, and we want to be able to see solar flares, and they're very different things. So you want to be able to see a solar flare which heats up the atmosphere of the sun to many millions of degrees, whereas the source of a coronal mass ejection might be a cool filament eruption. So it's important to get that balance between the different wavelengths.
And of course the fun part of it in a way is that you're looking at this really complex set of images at different temperatures writhing before your eyes, trying to pick out the ones that are more complicated, if you like, and try to predict an eruption or an explosion. And of course that's where we are at the moment. It'd be lovely to be able to say something is going to erupt tomorrow afternoon at 5 o'clock and it'll cause us a particle storm at the Earth. We can't do that yet.
I mean, SOHO actually observed the largest solar flare ever recorded, and it came from a sunspot region, or an active region, that was, I think, the biggest in 13 years, and it created a whopping X28 solar flare. Luckily it wasn't fully directed towards the Earth, so we didn't feel the full impact, but we did still get the particles and the radiation coming towards us.
You said it was an X28 flare. Some people won't know what that means.
Well, we have a scale of classifying flares dependent on how much X-ray radiation we receive at the Earth, and it goes from it goes through B, C, M, and then up until recently it stopped at X10, but this one was a massive X28, so it went completely off our scale.
I must give my usual warning here. Don't look straight at the sun, and never turn binoculars or a telescope towards it, even with a dark filter. If you project the sun, then you see sunspots. And what are sunspots?
The sun is a kind of a magnetic soup, isn't it? Just about everything that you see is driven by the magnetic fields. In a way, the sunspots are an extreme version of that, where the magnetic fields are really compressed together coming through the surface, and you're seeing a region that's actually effectively cooler. And it's just one signal of the active structures, if you like, that are there in the sun's atmosphere, and the complex loop systems lie above that we map in the ultraviolet light and so on.
We can tell, too, what elements are present in the sun.
Absolutely. The majority of the sun is, of course, hydrogen.
Oh, yes.
There's some helium there, of course, but the key for us in many ways are these trace elements, or actually trace ions. They're charged gases, of course. And in this movie, what we're looking at is at the edge of the sun, and the three different colours are in fact extracted from the spectroscopic data. The blue is oxygen, the green is from magnesium, and the iron is the orangey colour. And they're from completely different temperatures, so it's like putting the physics into it and producing weather maps within the sun's atmosphere.
So many people say the sun is simply burning, and that's a bit misleading, isn't it?
Absolutely. In the core of the sun there's the thermonuclear fusion occurring. The energy from that has to come out through the body of the sun, which is basically a ball of gas. Ionized gas, it's charged, so it's a plasma. Extremely hot, it radiates through the body of the sun, and as you get towards the surface you have convection. So if you look at the top of the sun from above, as it were, you see this boiling pan of water almost. It's poggling away, if you like, in front of your eyes. And you can see that looking in ultraviolet images. For
What is the
example.
core temperature?
Something like 15 million degrees. But the surface of the sun is only about 6,000. And the strange thing is that as you move up away from that surface, the corona gets hotter and hotter.
Why is the corona at such a high temperature?
Well, there are many theories, of course, and many people believe different things, but the bottom line has to be that you're getting energy, of course, from the body of the sun up into the corona, and the key is that if you look at the sun's atmosphere, in particular in ultraviolet images, extreme ultraviolet images, X-ray images, you see wonderful sets of loops, and the clue there, of course, is a bit like the old iron filings experiment at school where you sprinkle the iron filings
Yes,
on a piece
indeed.
of paper with a magnet underneath. You can see the loop structures, the magnetic field of that thing. And of course, in the sun, we haven't got iron filings, but we've got the gases trapped in those loops, the plasmas trapped in those loops, and they're writhing because they're all like elastic bands, if you like, rooted in the body of the sun.
Here on Earth, we see the corona with the naked eye only when the sun is eclipsed. But the thing is, space are different. You get amazing views there.
Absolutely. And this is one of the great unexpected delights of Soho, is that, yes, we can eclipse the sun with an instrument called LASCO, and we can see the outer atmosphere of the sun, the large-scale corona. But also, of course, we're seeing the stars in the background and these comets, and everything orbits the sun. And when the comets come very close to the sun and pulled in by the gravity, we've seen lots of them either making swing bys of the sun or actually seemingly meeting their fate, either burning up as they get so close to the sun or maybe even diving into the sun itself.
Also, we can see planets with Soho.
That's right. So, of course, we're looking towards the sun and we're seeing everything between the Earth and the sun, and then also things beyond the sun as well. And as the planets are going around the solar system, we see them orbiting the sun. So there's some great movies where you can literally see the planets coming in seemingly from both sides as the planets are going in orbit around the sun. So Jupiter, Venus, looking really bright, really beautiful in these images.
The interesting thing is, because they're so bright, the detector systems actually bleed effectively, so you see
Yes.
little lines as they come in. So because of that, we've even been accused that we're seeing UFOs, but it's
yes,
actually
of
the
course.
planets and the bright
That's
stars.
bound to happen. No flying saucers yet, and no Vulcan.
Oh, we'd be the first to
No
publish
Vulcan.
it.
As we all know, the sun is, to some extent, a variable star. We have the 11-year solar cycle. Well, you've not been through a complete cycle yet, have you?
Not quite, but
Almost there.
yes, almost there. Almost
Where
there.
are we now?
Touch
We're near minimum.
That's right. But I mean, even though we're going towards solar minimum, we're still getting some very, very large coronal mass ejections being launched towards us and massive flares happening. So the sun is still producing some really amazing events for us to study.
We're looking into the fundamentals of how a star works. So to a lot of us, solar minimum is really important, and the sort of things we're picking out are things like little explosions, little jets and so on tiny scales within the sun's atmosphere. These must be fundamental to the way a star's atmosphere works. So studying the quiet sun is important.
Well, we've learned a great deal, but we can't really say we totally understand the sun as yet, can we?
Not yet. I mean, I hope that it's not too far off now. I think in the future we have some really exciting missions that are going to be launched. We have Solar B launching next year and Stereo, and together those instruments will enable us to look better at coronal mass ejections, understand flares better, understand the atmosphere of the sun and how it links with the magnetic fields better. So I think, yeah, the future's definitely very bright for solar physics.
So we're learning more all the time. Soho now, 10 years old, going strong.
Absolutely.
The story is not over yet. Lucy, Richard, thank you very much.
Thank you.
Well, our sun is a star, officially a dwarf star, a very average star. And stars are very different sizes and very different masses. We know of stars that are big enough to fill the entire orbit of the Earth around the sun. Others are even smaller than the Earth. So the sizes of the stars cover a very wide range. And to join me now, two experts in this, Dr. John Mason and Professor Barry Jones. You know, John, I'm always surprised at the immense variety of the stars.
Yes, I mean, there's various different ways in which we can look at big and little stars. They're either big and little in terms of their mass, in other words, how much matter they contain, or they're big and little in terms of their diameters, how big they are compared with our sun or, say, a large planet like Jupiter. One of the problems with using diameter as a means of classifying stars is that for a star of particular mass, the diameter changes as it evolves. It expands and it shrinks. So we tend to use mass as the main means of classifying them. And I suppose it all begins with the way a star is born. Stars are born, of course, from huge, slowly spinning clouds of cool interstellar gas. this cloud starts to coalesce. It forms large globules, which we call protostars. And over a period of time, these globules slowly contract under the effect of their own gravity.
It does take time, of course.
It does take time, and the time varies depending on the size of the globule. Now, as these globules contract under their own gravity, the gravitational energy is converted to heat energy, and so it heats up the centre. Now, when the temperature reaches about 10 million degrees or so, nuclear fusion reactions begin in the core. Hydrogen is fused to helium, and the radiation pressure pushing out from that stops the contraction. And so the star then becomes stable, and we call that stable period of a star's life a main sequence star.
And the star spends a long time on the main sequence. I mean, our sun's a typical main sequence star now.
Indeed, our sun is a main sequence star, but of course the time a star spends on a main sequence, as we should see, varies depending on its mass.
The more massive the star, the quicker it evolves.
Indeed. I mean, you can compare a really massive star to a gas-guzzling car. It uses up its available hydrogen fuel much more quickly.
What are then the most massive stars of the main sequence?
Well, it appears that the largest amount of gas that can come together and not break apart into a number of smaller globules is about 150 solar masses. And this upper limit on the mass of a single star has recently been confirmed by some studies done using the Hubble Space Telescope on a giant cluster of stars called the Arches cluster. Now, this is a cluster about 10 times as big as a typical cluster of stars in our galaxy. It's 25,000 light years away. And when you look at this cluster of stars, you find very large numbers of low-mass stars, and only a few very massive ones. But it's those few very massive ones we're interested in. Now, there's always a snag when you're looking for really massive stars, and this is the point that we alluded to just now, that their main sequence lifetimes are very short compared with the Sun. The Sun will live for 10,000 million years on the main sequence. A star 10 times as massive as the Sun might only be there for 30 million years, and a 100 solar mass star for perhaps a couple of million years. So not only do we need to find a very big cluster, we need to find a young one. And fortunately, the Arches cluster is exactly that. It's just over 2 million years old. And when we look in the Arches cluster with the Hubble telescope, it turns out that the most massive stars we can find are about 130 solar masses, and they haven't found any bigger than that. And so there obviously must be a limit, an upper limit of about 150 solar masses.
Stars of that kind will be incredibly luminous.
Yes, they would. And in fact, there's some other observations of a star of about 150 solar masses called LBV 180620. It hardly trips off the tongue. It's a blue supergiant with about 150 solar masses. And this star is quite remote. It's 45,000 light years away on the far side of the galaxy, and yet it's still visible in binoculars at about 8th magnitude. And that's because it's 40 million times as luminous as the Sun.
That's a record so far.
It is a record so far, and I don't know whether we'll find any that are more luminous than that, but it shows you that the very massive stars are very luminous.
No, indeed, because they don't last for long.
No.
Let's go now to the other end of the scale. This is your field, Barry, these very low mass stars.
Indeed. I'm now going to go well down below the mass of the Sun. I'm going to go down to about a 12th of the mass of the Sun, which is about 75 times the mass of our giant planet Jupiter. I'm not going to go any further down in mass than that, because if you go down further in mass, the interior of the star never gets hot enough to trigger and sustain hydrogen fusion reactions, so they don't have a main sequence lifetime. Below about half a solar mass, they're called red dwarfs. And they're still stars, they're still burning hydrogen, but they are in fact very cool. If we go to the extreme end of the range at 12th of a solar mass, then the temperature, the surface temperatures, which for the Sun is about 5,500 Celsius, for these low-mass red dwarfs is only about 1,500 Celsius. They're also much less luminous than the Sun, about 10,000 times less luminous at this mass limit. But because they're not that hot inside, they only just about reach the 10 million Celsius temperatures necessary to have hydrogen fusing. And so this means they have very long lifetimes. They're very slow burners of their fuel.
Well, they've been there since the very early days of the galaxy.
Some of them would have been formed quite recently, but they'll certainly see, the end of the galaxy. They're going to live so long.
Let's go now even further down the scale.
Indeed. 75 masses times Jupiter, 75 Jupiter masses, is the lower limit for these red dwarfs. And we're now going to go down below that, and we enter the realm of the brown dwarfs. Now, the brown dwarfs are even cooler, 1500 Celsius and lower. Their core temperatures are such that they never reach that 10 million Celsius level where hydrogen will fuse to helium. They are failed stars. Their masses range from about 75 Jupiter masses down to about 13 Jupiter masses. Now, you might ask, well, why don't we just go down and down and down? Well, round about 13 Jupiter masses, something happens. Whereas brown dwarfs are fully convective objects, they're all mixed up inside. Once you get down to about 13 Jupiter masses, you begin to get separation. So that in Jupiter, for example, we have a core, we have a shell, we have an outer atmosphere. That's the distinction between 13 Jupiter masses and a higher. It's a structural internal difference. But in spite of this big structural change, one thing that doesn't change very much between brown dwarfs and giant planets is the size. Brown dwarfs have about the same size as giant planets like Jupiter. This is quite extraordinary. It's the mass of the brown dwarf that makes it a different object from a giant planet. And one, for example, has got the horrendous name, which I can never remember, called 2MASSWJ0036 plus 18. This is a very red, very dim object, round about a twelfth the mass of the Sun. So it's kind of brown dwarf, red dwarf, we're not quite sure. Now, if we want to know the mass much more accurately, we have to look at other places where we can find brown dwarfs, which is in binary systems. And here we have a very nice way of determining the mass, because if we have a star and a very faint low-mass brown dwarf, what will actually happen is that they'll orbit around their common center of mass. And if you can see both of these components and look at them and measure their orbital period, you can actually get the mass, not just of the star, but of the brown dwarf as well. But in order to do this, it's crucial, of course, to see the brown dwarf. And the big problem here is that to look at a brown dwarf next to a star, it's a bit like trying to detect a firefly, next to a searchlight. A very difficult problem, huge contrast problem. And it really is a difficult one to crack. But it's been cracked. And one is around the star AB Doradus A. This is known for some time to have a substellar companion, because the AB Doradus A does a tiny little orbit. It's, in fact, about 120 times less luminous than the main star. The first one to be detected was around a red dwarf star called Gliese 229A. Yes. And that was in 1995 by the 200-inch Palomar telescope, and I think it was confirmed later on by the Hubble Space Telescope. Now, the other way to detect brown dwarfs is in transit. You've got a star, and you've got the companion moving in front. And this will cause a apparent dimming in the star. And from this, you can find not only the mass of the low-mass stellar companion, you can also find its diameter.
Well, we talked about these very small stars. Now, the other end of the scale again, these very large stars.
If we look at the Sun, look at the future of a star like the Sun, or up to 8 solar masses, in about 5,000 million years, when the Sun has used the hydrogen fuel in the core, it will then start to fuse the hydrogen in a series of shells around the core. And eventually, as that process continues, the temperature in the core will become high enough to fuse helium, and that will produce ashes of carbon and oxygen. Now, these reactions going on in and around the core produce a considerable increase in the radiation pressure pushing outwards. The mass of the star hasn't changed, and so basically the whole star swells up. And as the star swells up, so the outer layers cool and it becomes red. So you get left with a very large star, 100 times the diameter of the Sun, but with cool outer layers that look red, and we call that a red giant. Now that's the way that the sun is going to evolve, and then the red giant itself is unstable. The red giant eventually has a rather loose grip on its outer layers, and it will shed those outer layers over a period of time. And the white-hot core becomes a star known as a white dwarf. Now, while the white dwarf is still shining, it will be surrounded by the outer layers of the original red giant star, and you will have these beautiful planetary nebulae. Now, once you've got your white dwarf, it's interesting to bear in mind that this is the core, the very dense core of the original red giant star, and that will be no bigger than the Earth, and a teaspoonful of that white dwarf material would weigh a ton. So it's really very, very dense material. So we have a sun-like star eventually shrinking to produce this Earth-sized remnant. Now, in the case of very massive stars, of more than 8 solar masses. Now these, of course, as we've said, use their available hydrogen fuel very quickly. They consume it at a prodigious rate. And at some stage, when the hydrogen fusion processes have run their course, because the star is so massive, you get a successive series of thermonuclear reactions that fuse successively heavier elements. And eventually, a core of iron will be formed in the centre of that very massive star. The fusion reactions very, very quickly cease. The radiation pressure that up to now has been pushing out and holding up the outer layers of the star just stops. And the star implodes. And as the outer layers of the star fall in, they compress the iron core to atomic density, producing a core of neutrons that is about 10 to 20 kilometres across. It then bounces, you get a shock wave rippling out through the outer layers, and all the outer layers of the star are blasted outwards, producing the supernova.
And we can see their remnants. And we must show the Crab Nebula.
Yes, indeed. The Crab Nebula, of course, is the remnant of a star that was seen to explode by the Chinese in 1054. It's in Taurus, of course, quite close to the star Zeta Tauri. And here you can see the expanding cloud of debris from the supernova explosion.
You can actually see it with binoculars, you know. Get Zeta Tauri in the field and you see the crab there as a tiny pet.
So in the case of these really massive stars, we get left with a very small remnant, 10 to 20 kilometres across, of nuclear density. And a pin's head of that material would weigh 1 million tonnes. So these are very dense. So we can see that at the end of the lives of both sun-like stars and massive stars, we get left with very small, low-diameter remnants. An Earth-sized white dwarf in the case of a sun-like star, and a neutron star the size of a large city in the case of the very massive stars.
What about the deaths of the very low mass stars? They're the red dwarfs.
Well, the red dwarfs, of course, have a huge, long main sequence lifetime, sort of, you know, thousands of billions of years. But ultimately, that main sequence lifetime will actually end, and then they'll just fade away from view. But that will take a very, very long time into the future. We don't see, the universe isn't old enough for us to see that happening yet.
So the stars are a very mixed bunch indeed, from the very large to the very small, from the very luminous to the glowworms. So they're a very varied bunch. Barry, John, thank you very much.
Thank you.
Thank you.
When I come back next month, we'll be talking about the edge of the solar system, if it has an edge. Till then, good night.